Greetings, my name is Carlos Guisao, and today I will be presenting to you about millimeter wave communications for 5G. Introduction. What are millimeter waves? Millimeter waves are radio waves that have wavelengths between 1 and 10 millimeters as extremely high frequency waves that exist in the terahertz gap. Millimeter waves are wave frequency bands between the infrared band and the super high frequency band. In 1990, an Indian scientist by the name of Chandra Bose was the first to investigate millimeter waves and their potential applications. Since then, the increased need for scholars and telecommunication practitioners have been increased. All of this because of the data rate demands for communication services has been getting greater and greater. And now it presents an opportunity for the usage of millimeter waves in the 5G wireless technology, which is being considered as a potential option. So what is the aim of this presentation? The main aim of my research is to point out the challenges that come with applicability of millimeter waves in the 5G wireless network technology and point out the potential solutions that could be used to solve them. Millimeter waves and the 5G network. 2G, 3G, and 4G network. According to an estimate done by Cisco, it is estimated that by the year 2020, there will be an approximate of 5.5 billion wireless networks users globally, and that each of these users will use just about 20 gigabytes of data per month. Thus, the current wireless technology might not be adequate to satisfy the data usage for this new era. So what is the difference between 4G and 5G? The main difference is the infrastructural cost, high capacity for high numbers of simultaneous users, and utilization of the untapped millimeter wave frequency gap. However, the most important aspect of 5G is the massive MIMO, which enhances the transmitting and receiving of more than one signal at the same time in the same radio channel with multiple antennas. So what is the massive MIMO? The massive MIMO is a tech which is being used by known companies such as Facebook, ZTE, and Huawei, all which managed to develop network channels with the number of channels falling between 96 and 28 channels. This facility reduces latency, increase data rates, and increase capacity for requests processed per unit time. Millimeter waves, interference, and loss. Now, since millimeter waves have gained much attention and interest due to its potential for the incoming 5G wireless net technology, the efficiency is highly hampered by the high signal attenuation during transmission, which makes them susceptible to attenuation during transmission during rain, atmospheric gases, and free space propagation. Losses due to propagation in the free space. So, in order to better understand millimeter waves, it is important to review the background theory which displays the relationship between power and frequency developed by the free transmission equation. You can see PR is the transmitted power, while PT is the transmitted power, and PR is the power received by the channel. GT is the overall gain of the transmitting antenna, while GR is the overall gain in receiving antenna. Lambda is the wavelength of the signal being transmitted or received, while R is the distance between the receiver and the transmitter measured in meters. Assuming that the signal is being transmitted in free space and that the gain GR and GT are isotropic, the power signal transmitted spreads out from a point antenna into space. As shown in the Friis equation, attenuation refers to the power loss that occurs as a result of the power spreading out from the point antenna as it propagates towards the receiving end. In this case, attenuation is occurring as a result of free space propagation. Now, since the distance between the receiving end and the transmitting end determines the quality of the final signal receiving, the Friis equation states that the greater the amount of the wavelength, determines how great the power received will be. If the wavelength is greater, it implies that the frequency of the signal is reduced. Now think about it. Since the millimeter wavelengths are characterized by having high frequency, attenuation is increased due to free space propagation, and the signal power loss for every meter is huge in any millimeter wave. However, it is also noted that since antenna gain is directly proportional to frequency, many antennas can compact a small effectual area, hence allowing for massive MIMO transmission. So now let's talk about absorption by water and oxygen. Another critical transmission characteristic of millimeter waves is their tendency to undergo absorption by the water and oxygen molecules in the atmosphere. But not the entire wave is susceptible to atmospheric loss. Those frequencies bands that are susceptible are the 57 GHz and the 64 GHz, after reaching 100 decibels per kilometer. However, the attenuation levels beyond these two bands are negligible, and therefore 5G network will be using millimeters beyond the frequency band to eliminate attenuation for water and oxygen reasons. Rain. Now, the diameter of a raindrop is roughly equivalent to the wavelength of millimeter waves, and when a millimeter wave hits a raindrop, it scatters and loses its power. When there is a heavy rainfall, attenuation of 28 GHz, wave averages 20 km per hour, it's only 7 decibels per kilometer. But when there is a 73 GHz wave propagating through the heavy rainfall with the same characteristic, the attenuation is only 10 dB per kilometer. Now, the attenuation reduces further when cell size of 200 meters are considered, which then solves this issue by using an attenuator that can be easily managed through the use of smaller cell size. Millimeter wave blockage. The ability for a wavelength to penetrate a solid material depends on the wavelength. Now, since millimeter waves have short wavelengths, it has issues penetrating solid materials such as wood, walls, human beings, glass, etc. This aspect makes millimeter waves quite inefficient for communication over long distances where solid blockages cannot be controlled. This is a huge problem for millimeter communication, and we'll discuss the potential discussion solutions next. Potential solutions. Beamforming. Beamforming is the signal propagation technology in which the best signal delivery route is identified in order to reduce interference from other users as well as objects. This potential solution would solve issues regarding free space propagation. Now, as discussed before, free space propagation affects millimeter waves since they are more susceptible to quicker rates of signal. The main goal of beamforming technology is to focus the signal and all of its energy in certain directions, probably a direction in which a receiver unit is located. Therefore, beamforming perfectly addresses the problem of free space propagation. Collection of non-line of sight signals. Now, we have seen before that millimeter waves are absorbed by solid materials because of their short wavelengths. Furthermore, this is a big problem that millimeter waves are currently facing. A possible solution would be to use non-line of sight communications. Now, the way that this works is by taking a look at each link, and every time a link breaks, then the transmitting channel must rapidly explore the various beam directions to identify obstacles that might have caused the link breakage. In this way, the receiving channel can accrue some important link information in order to maintain the quality of the receiving signal. Beam tracking. Beam tracking entails the process of mapping the propagation of a set of beams of waves in order to predict propagation characteristics, hindrances, and blockages. Beam tracking is especially designed to reduce the tendency of millimeter waves to be absorbed, blocked, or scattered. Beam tracking often employs data mining and machine learning concepts to develop algorithms that accurately trace out a particular wave propagation path with least attenuation. While beamforming essentially minimizes propagation losses in free space, beam tracking minimizes propagation losses via blockages and attenuators. With accurate training, beam tracking is much more effective than beamforming. So, if you guys have any questions, just post them on underneath the video. And well, that's it. Thank you very much.